Okay, so we can get started with the next talk. We have No Code Change GPU Acceleration for your Pandas and NetworkX workflows by Rick Ratzel and Ramasubramani. You can get started.
Hi, yeah, thanks for sticking around. Last talk slot of the day before lightning talks and poster session. I'm Rick Ratzel. I work at NVIDIA with Ramasubramani, and we work on the RAPIDS team. I work on the cuGraph library, and Vyas works on cuDF, and we're going to be talking about no-code change GPU acceleration for Pandas and NetworkX using those two technologies between those two libraries. Thanks. So many of you have probably seen this graphic before. It's circa 2015, I think, here, yeah. The scientific Python stack. These are a collection of libraries, probably not all represented here, that are available in the toolkit of any data scientist. They've kind of earned their place there for being very easy to use and popular and powerful. And today we're going to talk about specifically NetworkX and Pandas out of these. To kind of demonstrate that, we're going to take a somewhat typical application that you might think about. The question being, can you rank in Wikipedia all the editors based on the importance of their contributions? That's pretty much all the code there. I'm not showing the code that actually parsed the XML wiki dump. That happens every so often. The one that we used was from June 20th of this year. And all the code, by the way, is in that GitHub URL. But that's pretty much it, though. And once the dump files are in, or once the extracted files are in place, there's some CSVs which are being read here in the script. That's pretty much all the code there, and it's using Pandas and NetworkX. And you can see kind of the demonstration of how useful and powerful they are, because I was able to answer this question using just those lines of code. What we did here was we read in roughly 10 gigabytes of CSV data, which represented 21 million nodes in the Wikipedia graph and 315 million edges. And the total runtime for that was 52 minutes, a little over. What it does here is it reads those CSV files in. It creates a graph using NetworkX. It runs PageRank on that entire graph. Using those PageRank scores, it takes those and applies those to each editor. And for each page that editor edited, it adds a cumulative score of using the PageRank score for that page. So it's kind of a rough idea of the importance of their edits. So the whole point of the talk, though, is not to kind of critique the method we used. It's more to demonstrate the libraries using a kind of a made-up metric here. But either way, it was a pretty informative script that was based on real-world data. And the idea being that this is pretty accessible, common everyday topics that are, useful in conversations today. So being 2024, there's a lot of data here, and these libraries are very popular. They need to keep up. Using 52 minutes to do this analysis is okay, but it would be a lot better if it was faster, clearly. Now, Pandas and NetworkX are the most popular for these applications, but many other options do exist, and they're faster and or different or more powerful in different ways. But for whatever reason, they're not as popular. Pandas and NetworkX have these well-known performance limitations, but despite that, they still get more usage because the alternatives are less familiar. They have probably a smaller community. They're just not quite an unofficial standard like the other ones are. You can even ask ChatGPT, kind of an informal metric here, but what we did here was we asked simply, how do I join two tables in Python? And the first thing it did was it says install Pandas. Likewise for NetworkX, I asked it a question about graph analytics. How do I find the between the centrality scores for every node in a graph? In this case, I didn't even say Python. And it said step 1, install NetworkX. So that kind of represents, NetworkX being not just the most popular within Python, but probably the most popular graph analytics library in any language. Likewise for Pandas, data frames aren't unique to Pandas, but it's still promoting Pandas.
So we had that first slide showing, the scientific Python stack, and clearly there are a couple of APIs here that are very popular, and people are preferring to use them regardless of what else is out there, even if they are seeking speed, right? And so our answer at NVIDIA was to say, well, if people like these APIs, let's build a bunch of tools that look exactly like the APIs people like, but perform better, that run on the GPU. And so NVIDIA's answer to this is the Rapid Stack, which is a whole suite of tools that accelerate your entire data science and ML pipeline, everything from data processing with data frames to graph and machine learning algorithms. Today's focus is going to be on graphs and data frames, so we'll be talking about QDF and QGraph. So what is QDF? QDF is our accelerated data frame library. It provides you GPU-accelerated data frames that look and feel as much like pandas as possible. And when I say as much as possible, you can see sort of the scripts there on the right. Really, all you have to do is change your imports, and things just work. Of course, it's never quite that simple, but we'll get to that a bit later. However, in this case, with these sorts of simple changes, you get to see pretty large speedups, right? Now, we've already established that Pandas and NetworkX aren't exactly the fastest tools in the toolbox that are available to you, but if we do use them as your standard, and you compare here, you see a pretty huge speedup using QDF versus Pandas, up to 2 to 3 orders of magnitude, and you get a pretty large coverage of the Pandas API, pretty much all the standard things that people want to be able to do, joins, group by aggregations, user-defined functions, things like that. Similarly, QGraph offers the same sorts of functionality analogous to NetworkX, but again, operating on the GPU. In the case of NetworkX, again, you can see you don't really have to make big changes to your script. All you've got to do is change your imports, use QGraph instead of NetworkX. In this case, we're also showing how it works with QDF, so there's an extra one-line change. But again, for the most part, things work about as you'd expect. And you see, again, the large performance gains that you could get. In this case, we're not really showing the largest scales, which is where NetworkX obviously is going to show the biggest performance gaps with QGraph, especially given that so many of the graph algorithms are, scaling not just with n, but with polynomials in n. So we have these new APIs. Are we done? Well, we get to this point, and as Rapids, we looked around and said, we have these libraries, they're fast, they look a lot like QDF and NetworkX, like Pandas and NetworkX, but they still aren't seeing quite the uptake that we would like. Not as many people are using them as could be. And so why might that be? So for that, we're going to turn to this little analogy of swim lanes, right? So imagine for a moment that you've got a nice swimming pool out there. I'm swimming over in the slow lane, trying to flounder my way through. And over in the fast lane, you've got Michael Phelps going, right? Now, for a moment, forget how I ended up in the swimming pool with Michael Phelps. You want to make sure that you give me the noodle I need so that I can float my way to the other side, but Michael Phelps has the super hydrodynamic swimsuit he needs to shave off those fractions of a second he needs to set the new world record, right? So how do you achieve that? Well, in this analogy, the people in the fast lane are the CUDA kernel programmers, right? The people who write the fastest possible code for some cutting edge application. And they need to be able to write raw kernels, but you also want to be able to empower them to do this, hopefully in ways that reduce the number of times they have to reinvent the wheel. And for those of you who have written CUDA kernels, but haven't really kept up too much with developments in this space, I'd really encourage you to look into all of the great libraries in C++ and C that have been developed in the last few years to make kernel programming easier, things like Thrust and Cub, right? So again, you have these kernels and you have these libraries, but this is SciPy. People here want to be writing code in Python. So can you write these kernels in Python? Obviously, there's a bit of a performance hit, but the answer now is certainly yes, right? The two most popular tools for doing this are Numba. Hopefully, most of you have tried this out. You can write Numba CUDA kernels with Numba. CuPy also lets you JIT kernels. And if you were in the room about a half hour ago, you would have seen our talk on Warp, also by a fellow NVIDIA engineer, talking about how we can use Warp for the same purpose. Now, this is great. It's in Python, but it's still writing kernels. So what can we do that doesn't require you to know how a GPU works, but instead just use the GPU writing code that's familiar to you? That's sort of where the Rapid Stack comes in, right? All these tools like QDF and QGraph. all you have to know is that your familiar APIs, things like scikit-image or scikit-learn, use our tools instead, and things will just run. You don't have to learn something new. So what's the gap here? What's the gap between taking ourselves from this sort of middle lane to the slow lane here that helps as many people as possible with a little bit less code acceleration? Well, there's two major problems, right? One issue is that despite the fact that it's very similar, it's still not quite possible to take the code that you wrote and run it in different environments and test it, right? Scripts that use QDF need to be run on a system with a GPU because it will immediately fail if you try and run it and there's no GPU available. There are there are packages out there that don't have this kind of limitation that support multiple architectures, right? You can take the big deep learning tools as a good example. Tools like PyTorch or TensorFlow can target a given device by simply changing a couple lines of code, say run on the CPU or run on GPU 1. And this allows you to prototype code locally, then copy it up to whatever server whatever cloud you're running your large-scale models on, and have it run there. The other issue that we run into is that it still requires non-zero code change to go from using Pandas to QDF. You have to change some lines of code. In the simple example I showed you before, it was just a matter of changing your import. But in more complex examples, you might have to change small things because of incompatibilities. And so that's where we really get to the lane that we're trying to talk about today. How do we achieve no code change acceleration? And that's where QDF.pandas and NXQGraph come in. So what is QDF.pandas? QDF.pandas is our zero code change approach for accelerating your pandas code. And when I say zero code change, I mean if you're in a Jupyter notebook, you load an extension. If you're running a Python script, you just add -m QDF.pandas and things just work. You no longer have to make any changes to your script. You can test it locally using pandas and then copy it up to your cloud and just add -m QDF pandas and it will run on the GPU. And it will give you pretty much the same performance benefits that you would have gotten if you'd had that running with QDF. So how do we do this? Well, this part gets a little bit tricky, but essentially what we've done is create proxies for the pandas module so that anytime you import pandas, you instead import our proxy module. And this returns you, again, a set of proxy objects that know how to transfer data back and forth from the GPU and know how to run algorithms on the GPU. This allows you to essentially run anything on the GPU that we support, but to fall transparently back to the CPU when we don't support it. This is a little bit of an aside from today's talk, but I just do want to drop a little bit of a mention that coming soon to us, we'll also be having a similar experience for polars. So that for those of you who are polars enthusiasts out there, we will have a no code change experience for polars as well. Now, one of the most popular features of QDF Pandas is the profiler. Like any other profiler, it tells you how fast your code is running, but really the goal of this profiler is not just about telling you how slow or how fast your code is, but it's to tell you which parts of your code are running on the CPU and which parts are not. And conveniently, it will provide you a little link to open an issue. So if it turns out that you found a function that doesn't run on the GPU and you think it should, please try it out and let us know. How do you use it? Well, if you're in Jupyter Notebook, again, just use a Jupyter Magic. If you're in a script, it requires adding a couple of extra lines of code. All right, so I mentioned that we do this with these proxy modules, right? This slide gets a little bit into the details for those of you who are interested. What normally happens when you import a module is Python looks through a bunch of directories and searches for either a file or a directory with the name that you've requested, and it returns the first one that it finds. But it does allow you to preempt this search by inserting what's called a metapath finder somewhere into the sys module. So what we've done is basically when you run with python-mqdf.pandas, we insert a module metapath finder that searches and finds our custom module accelerator. The accelerator is actually pretty general. It doesn't have to be QDF and pandas, but right now that's what we've exposed. And so you can see in that snippet on the screen that it says, well, when you imported pandas, what you got back was an accelerated module that the fast version is QDF and the slow version is pandas. And anytime you try and access attributes from it, it'll try and give you a QDF version but if it can't, then it gives you back a Pandas version. Now, that's how you get modules out. What happens when you actually access parts of this module? Say, like, you ask for a data frame from Pandas. Well, for that, we also have these proxy objects. So every module that you get out of qdf.pandas returns objects that are proxies that know what their corresponding fast and slow types are. In this case, you can see at in the first snippet there that these things masquerade pretty closely as Pandas objects. If you check most of their standard attributes, you won't be able to tell. But if you know where to look, you'll see that these objects are instances of this custom fast-slow proxy type. And that really is hiding this detail of, okay, if you request like pandas.dataframe.apply, try to run this on a GPU using QDF. If it fails, come back and run it on a CPU. Now, there are some fundamental limitations with this approach. We know that we can't proxy C API calls, for instance. And also, we're not terribly happy with the fact that this sort of hacking behavior of import is the way to do this. And so we're certainly looking for better ways all the time, and we're working with the community. But clearly, this serves a need, right? There are plenty of people who have Pandas code that they can't or won't be able to change in the near future. And so this is an easy way to give people quick acceleration.
All right. And so like accelerated pandas via qdf.pandas, we have accelerated NetworkX via NXQGraph. Same concept, works quite a bit differently internally. I'll talk about that in a minute. But the exact same experience. Zero code change GPU acceleration for your NetworkX code. You write it once, you can run it on a CPU-only system or on a system with GPUs and get acceleration. And the acceleration varies, obviously, based on the algorithm and the graph size. But we have here, you can see potentially up to 600x speed up depending on your use case. This particular graph here is this chart is demonstrating the between centrality algorithm on a fairly large graph. And as you increase the value of k, which represents the number of shortest paths searched, it just improves over NetworkX by, here we're seeing over 600x. So we have support for 60 popular graph algorithms. We probably add 1 or 2 each release. From that code snippet, which you can run, it's all complete there. You can see without acceleration, that run took 7 minutes, 44 seconds. You turn on, just set the environment variable, and now it's running at 20 seconds. Very different internally how it works compared to QDF Pandas. In this case, NXQGraph is the name of the NetworkX backend that we use here. Backends were supported in NetworkX 3.0. They were introduced, and they basically provide a means for an alternate implementation to be used instead of the default Python-based implementation that NetworkX ships with. You can have multiple backends installed on one system, and you can use both of them in the same workflow. That backend priority is set by the user with that environment variable. And basically, NetworkX will check, it's kind of like a plug-in system, if you will. If any given function is called, it will see if any of the enabled backends can handle it, and it will use that priority order to call them and return the results. If none of them can satisfy the call, it falls back to the default implementation. So you can imagine on a CPU-only system where there's no GPUs available, that same code would just run in pure NetworkX mode, unless you had another backend installed for that environment that would work. So now that we have these two approaches, we can revisit our initial application with both of them enabled to get full acceleration for both the Pandas parts and the NetworkX parts. So as Vyas mentioned, to enable QDF Pandas, you pass the -m flag to run the script through the qdf.pandas module. For NetworkX, you just set the environment variable. So here we're going to do both. And what we've done is we've seen that total runtime go from 50-ish minutes down to 22. So it's a decent 2.5x speed up. Why couldn't this be faster, though? Well, there's a few reasons. The QDF Pandas parts, they ran well. You can see the various operations have been done here, and they're ranging from 3 to 20 to 200x speed up. The NetworkX parts, the PageRank call in particular used to be the most expensive. It's now showing a decent 10x speed up, but the graph creation actually got slightly slower. It is now at 18 minutes, still dominating the runtime here. Now, it is 2.5x speedup isn't bad, but we have some work to do still. So if we look at this a little more closely, we can see that, among other things, cuDF.pandas has a high memory footprint. One of the workarounds we had to do for this example was read only half of the Wikipedia revision history. This avoided an out-of-memory error we got, and this is ongoing work for cuDF.pandas. Also, the handoff between cuDF.pandas and NetworkX is not optimized yet. By default, that's not accelerated. The reason being is that we need to return graph objects using the default NetworkX Python-based dictionary approach in order to support fallback for any given operation that's not supported by a backend. So we basically always have to have that Python NetworkX dictionary-based graph available, and that's very expensive to create still. Also, that PageRank call is, it's 10x faster, not too bad. But if anyone's familiar with cuGraph, they'll know that PageRank runs much faster than that. The reason it's only 10x here is because we have to take that initial NetworkX-based graph and convert it to a graph on the GPU and transfer it over there. This was a pretty large graph, so that took a while. The good news is that conversion's cached, and if the graph doesn't change, it can be reused. What we did was reran PageRank again just to demonstrate the speed. And at that point, the call came down to 10 seconds, so 190x speed up. And if any subsequent NetworkX call that NX cuGraph supports is using that graph, it'll also take advantage of that cache conversion, and they'll be much faster. Now, if you're willing to make a few code changes, we have another version of the script that we're calling a low-code change approach. So instead of using cuDF.pandas, we're just going to use cuDF. Its API is very similar, so it almost just drops in. Even nicer for NetworkX, that graph creation step, like I mentioned, is not accelerated by default. But if I specifically force it to be accelerated by adding a backend keyword arg and saying use the cuGraph backend, I will generate a NX cuGraph graph object, which is duck type compatible with the NetworkX ones. But if you try to call a NetworkX function with that graph that isn't supported by NX cuGraph, you'll get an error. For our example, all of the calls are supported by NX cuGraph. So it worked out well, and we ended up getting the total runtime for this workflow down to 32 seconds, which represents a 98x speed up over the original 52-minute runtime. Same exact results too. So the real takeaway here is that it not just, obviously makes your workflows run faster. That's obvious, I guess. But what it really does is ends up changing how you work. Because now that I can run a PageRank call in just a matter of seconds, I can run many, many PageRank calls with different options and answer even more questions. Because I found even doing this example, as I got more information out of Wikipedia, every time I got results, I had more questions. And I wanted to kind of probe at it even more. So of course, it wouldn't be a Wikipedia kind of based demonstration without doing the 6 degrees of Kevin Bacon, but it's SciPy, so we'll do 6 degrees of SciPy. How is SciPy connected to any other topic in Wikipedia via 6 degrees of separation? The first thing we did was we ran shortest paths, starting with SciPy to all the other nodes in the graph. Unaccelerated, that took over 7 minutes. We turned on NX cuGraph, and we got a decent 3x speed up. So we print some random topics here. How is SciPy connected to orange juice? Well, it is, and you can see the way it is connected there via that path. What about some random, Lake Leon in Florida? Well, who would have guessed that Dave Chappelle is responsible for making this connection? I wouldn't. And then Kevin Bacon, too. There he is. He is connected to SciPy via only a few degrees of separation. So, just for fun, I was able to do this in just a few seconds. So, again, if I had to wait an hour just to get results, I probably wouldn't have even explored this data this way. So with that, that's our presentation. We have some relevant resources up here. Here's all the GitHub repos that you can use to download the software. It's also available, of course, from Conda and pip installs. The code from this talk's in that repo. And then here at SciPy, we have a accelerated Python BOF coming up. And then we have a poster session, too, right after this. Well, not right after, but later today, It's right over there, actually. So you can meet us over there and talk to us more about NetworkX, and we'll answer cuDF Pandas questions too.
Thank you. A round of applause. Okay, now we can get to questions. We have one on Slack, which I'll ask. Why is the low-code change option faster than no-code?
Right, yeah. The low-code change option allows us to, well, in the case of NetworkX in particular, it allows us to bypass a lot of the assumptions we have to make, or it allows us to make more assumptions about being specifically for the GPU. In that case, we don't have to do things like create the Python-based NXQ graph, or sorry, the Python-based NetworkX graph in memory. And then we can also take advantage of the various on-device arrays, especially coming from cuDF Pandas, and just use those directly. We don't have to do as many transfers and things like that. And then for cuDF Pandas, I believe a lot of the failover mechanisms don't come into play. We're just using cuDF directly. So that helps speed things up quite a bit too.
Any other questions? Please raise your hand.
Yes, thank you for this talk. If my notebook has functions that are maybe they work only on CPUs, but I have some functions that could work on GPUs, when I annotate the notebook with Pandas, how would you know whether to use the CPUs or GPUs?
Yeah, so the way that cuDF Pandas works is that every API call, it basically searches to see if there is a GPU accelerated version, and if it's possible, it will run it. And so if you have a sequence of calls where, say, like 8 out of 10 of them will run successfully on the GPU, but 2 of them won't, it'll basically try all of them on the GPU. When it hits the one that doesn't work, it will fail. It will fall over, push the code over to the CPU, run it again, and then it'll try the next one. And if the next one runs successfully on if the next one will work on the GPU, then it brings the code back to the GPU and runs through it. So you can imagine that if you have a script where 9 out of 10 calls actually don't work on the GPU, this will actually be slower than if you ran it with cuDF. But almost all of the sort of core computational algorithms that we care about in Pandas are enabled on the GPU, so most of these will run through.
That makes sense. Thank you. And just one quick thing. Not all GPUs are compatible, right? So could I run this and annotate my notebook on a Mac? I guess not.
Yeah, this only works on NVIDIA GPUs.
Okay.
And yeah.
Any other questions? Okay, if not, thank you so much. We have a break now, and lightning talks start at 5.